Awesome. You guys are great. Man, I love the farmer's market. All right, let's see what's on my list. Carrots, potatoes, apples. Oh, it looks like they've got it all over at that MFA booth.
And then 0 says to 8, nice belt.
That's a good one. And hey, thanks for the onions. They're hip to be square.
Oh, you're killing me, Smalls. All right, Big Ed, thanks for coming by. I will catch up with you later.
Pete, what are you doing here?
Oh, hey, Noah, what's up?
I came down to the farmer's market to pick up some vegetables, but I didn't expect to see you working here.
You didn't? Who else would be running the booth for the Mathematical Farmers of America?
I would have said Farmer John von Neumann, but I guess now I have to say you?
You do. And if you're looking for some veggies, you are at the right place.
Oh, well, I actually do need some root veggies for the side dish I'm bringing to the math club potluck. But I gotta tell you, Pete, these vegetables look pretty weird. These carrots don't seem round enough. Like, they're not round at all.
Oh, that's because they're not supposed to be round. Here at the Mathematical Farmers of America, all our vegetables have square roots.
Square roots. Okay. But what's this?
That's a square rutabaga. Cool, huh?
Yeah, cool, but also weird. So, how do they taste? Because if they're not delicious, I don't think anyone's gonna care what shape they are.
Oh, they're delicious, trust me. And looking at your list here, I think we've got everything you need.
Great. But before you bag it all up for me, I have a question for you. Do you have any cube roots?
No.
You don't?
But we have a wide selection of cube fruits. Check out this orange. It's perfectly cubical.
Whoa. It's like a giant 6-sided orange die. Hey, do you have a 12-sided grapefruit back there?
Noah, do I look like I have a dodecahedral grapefruit?
No, but you look like you are a dodecahedral grapefruit.
Ha ha, very funny. All right, I got all your veggies bagged up. Anything else?
Yeah, one more thing. What's that picture on your shirt?
Oh, this? It's a joke, see? It shows what happens if you try to make a round pie with a cubical apple. You get a sphere.
Dude, you are such a nerd.
Oh, yeah? Well, so are you. I'm not the only one in the math club, you know.
Keep wearing shirts like that and you might be.
Hey, Noah. Welcome back to the math club and Happy New Year.
Happy New Year to you too. I trust that you had a nice and relaxing break from both work and the podcast for a few weeks here.
Yeah, I did. I was in Tennessee for, I don't know, like 8 or 9 days. We were visiting my parents. We saw my sister and her family. It was actually really, really nice. We got back to Washington on the 2nd and, of course, stepped right back into work. But, you know, it's the weekend. And so I'm feeling kind of relaxed. How about you?
Well, first of all, your holiday break sounds awesome. We also did a little bit of traveling. We went to Albuquerque to visit my wife's parents and sister, and our nephews and niece also came to Albuquerque. So it was a big family get together at the holidays, which was really nice. We got back on the 29th and did not jump right back into work. We're both teachers. And so we had the following week off and are just now getting back to work and happy to be back here in the math club with you.
That sounds awesome. It sounds like you guys really enjoyed yourselves and good for you for having a nice 2-week break away from work. You guys will get back in the classroom and back on campuses and you'll have a bunch of new energy, which is fantastic.
Yep, I am looking forward to it. I'm also looking forward to talking with you about square roots today. So why don't we get started?
Yeah. And I thought I would start with a little bit of a story. So at the end of November, I got pulled into a family movie night because my 8-year-old really wanted to watch Leo, which is this new animated film starring Adam Sandler and Bill Burr, and very funny and very cute. I don't know if you've seen it, but it's worth checking out.
I've heard of it, but we have not seen it yet.
Well, it's very good. And at one point in the movie, one of the characters just kind of busts out with this question.
What's the square root of 91?
And I won't tell you the setting for why she asked this. It's kind of funny. But unfortunately, the movie didn't answer the question. It just left us hanging.
Well, I would guess it's somewhere between 9 and 10 because 9 squared is 81 and 10 squared is 100. 91 is pretty close to the middle. So I would say it's about 9.5.
Yeah. Well, what I did was I rolled up my sleeves and I actually computed an approximation by hand. And what I got was 14,767 over 1,548.
Oh, brilliant. What does that reduce to?
Well, I'll tell you, there's a reason why I ended up with a fraction, but I did convert it. I actually used a calculator here to help me convert it to a decimal, but it is approximately 9.539405, et cetera.
Oh, well, congratulations. You did all this work and got approximately 9.53 something. And I did no work and got about 9.5.
Yeah, but I'll tell you what, if you and I both have to fly a rocket to the moon, I'm going to trust my calculations to be better off than yours.
All right. Granted, when Elon comes a knocking, we'll let you be the one that goes with him.
Oh, I don't let him in the house, actually. So we'll have to talk through the door.
So I noticed that even your answer started with the word approximately. So how close do you think your approximation is?
Yeah, well, I computed that as well. And if I square that result, if I take 9.5394 and so forth and square it, I get 91.000260 and so forth. So it's accurate all the way out to the 10,000ths place, which is pretty good for just some handiwork.
Yeah. You got very, very close. I also got very close with about 9.5.
All right, hotshot. We get it. You came up with a pretty good answer. So you may be wondering, all right, well, Noah just kind of winged it and got close.
You can be my wingman anytime.
Pete did a calculation and got closer. How did Pete do it? What was the calculation?
Yeah. I was wondering what you did that gave you that giant fraction that you ended up with.
Well, I used an algorithm that goes back some 2,000 years and is due to a Greek mathematician named Heron of Alexandria. Now, he may not have been the first one to discover or utilize this algorithm, but it's the first written account we have of it, and it appeared in a book that he wrote called Metrica.
Is this algorithm simple enough that we can explain it on an audio podcast?
Yeah, in fact, it is. And that's exactly what I'd like to do. And I thought that we could simplify our starting point by, instead of using the number 91, we could use something that's a little more friendly. In fact, I'd like to start with a number that's a perfect square. So it has a whole number square root. And I thought maybe we could start with the number 36.
All right. This sounds like a fun exercise, but before we get started, let's just real fast refresh listeners' memories on what squares and square roots are, just to make sure everyone's on the same page going into this little calculation.
Yeah, sure. And the cool thing about the words square and square root is that they are very visual in the sense that we can picture something concrete and geometric while we talk about the concepts. So let's start with the square. What is the square of a number? Well, if I take a number like 2 and I multiply it by itself, I get 4, and that is called the square. And we can picture an actual square whose side lengths are 2, and its area is equal to 4.
That makes sense. And so following the same logic, that would mean that 3 squared is 3 times 3, or 9, and 4 squared is 4 times 4, or 16, and on and on and on, right?
Exactly. And square roots are the exact opposite. So our opening question, what is the square root of 91? That's like asking, Noah, if I give you a square, a geometric square, whose area is 91, can you tell me how long the sides are?
That makes sense. And I also noticed that when you take the square root of 91, you're not going to get a whole number answer. Like the square root of 9 is 3, the square root of 16 is 4, but the square root of 91, well, as we just said a few minutes ago, it's about 9.5. So square roots don't necessarily have to be whole numbers.
Right. In fact, the only numbers whose square roots are whole numbers are the so-called perfect squares. And those are the numbers 1, 4, 9, 16, 25, 36, and so forth. And any other number, if you compute its square root, you're likely to end up with a so-called irrational number, a number whose decimal representation is infinite and non-repeating.
Okay, that makes sense. And I think that also explains why you chose 36 to use as our first example, because 36 does have a whole number square root, which is 6. But let's go through the calculation and see how we would get that if we didn't already know it.
Yeah. Now, you pointed out a word that I used a few minutes ago, and that's the word approximation. So the method that we are utilizing here, this method due to Heron of Alexandria, never will produce an exact value. It will only ever produce approximations. And that's even true if we start with a number like 36, which is a perfect square. So we'll illustrate this, but again, it won't produce an answer of 6. It will lead us in that direction, but we'll never get to 6.
Okay, well, I'm going to tell you right now, a question that I have heading in is, well, what good is this algorithm if it doesn't give us an exact answer? But I'm going to hold on to that question and ask it again after we've gone through it and see what I think then.
Perfect. Okay. Now, you and I both did the same thing, actually, when we were thinking about the square root of 91, which is we started with a guess. So let's make a guess at what the square root of 36 is. And let's pretend for a moment that we don't already know that the answer is 6.
All right, let's return from La La Land because that ain't gonna happen.
So I'm proposing, let's make an initial guess of 4.
All right, I'm guessing that the square root of 36 equals 4.
All right. Now let's check and see if we're right. How can we see if our guess is actually correct?
Well, I think the most obvious answer would be to multiply 4 by itself and see if we get 36.
Yeah, let's square it and check, right? So go ahead and do that for us.
Okay, 4 times 4 is 16, not 36. We undershot, so 4 is too low.
So 4 is too low. Okay, so thinking about what our next steps might be, give me an idea of what you could try.
I think I would take a higher guess and see if we get closer.
And how would you generate that higher guess?
Well, I could just start going up by 1 and go to 5 and see how close that is, or I could jump up a few. And if I end up overshooting, I'll have a range that I can start narrowing in on it from.
Yeah, and that is a very sensible thing to do. But you'll notice there's a lot of wiggle room in what you said. Well, I could go up by 1, or I could go up by a couple. Yeah, I don't know. Well, what Huron's algorithm gives us is a very particular way to generate additional guesses.
What I do have are a very particular set of skills.
And that's where part of the power of this algorithm comes from. It eliminates the need for guesswork and it gives us some precise targets.
All right, so what does Huron's algorithm say our next guess should be?
Well, the first thing we're going to do is we've observed that 4 is too small and we'd like to generate something bigger. Well, one way to do that would be to take 36 and divide it by 4. In other words, there is some multiplicative partner to 4 that I can use to multiply with to generate 36. And in this case, what is that multiplicative partner?
Well, in this case, I think we lucked out because it happens to be a whole number and it's 9.
Yeah, 36 over 4 is 9. And spoiler alert, this is not us lucking out. This is Pete picking the numbers that he wanted so that the answer would be nice.
Ah, you rigged the game, Littig.
I did. Guilty. I did it. But okay, we now have 2 numbers that multiply together to produce 36. Notice if we had the exact square root and we asked for its multiplicative partner, what would we get?
Itself.
We would get itself. Exactly.
I think maybe I kind of see where this is going. So if we know that 4 times 9 is 36, every little bit we move up from 4, we also have to move down from 9. Not in a linear way, but in a way that multiplies together to make 36.
Exactly. So the metaphor that I've got in mind here is I'm picturing a teeter-totter. And when I pick 4, it's too small and its partner is going to be bigger. So it's like the teeter-totter has the 4 on one side and the 9 on the other side. And since 9 is bigger and let's say heavier, we can picture its end down on the ground and the 4 up in the air. Now, as I adjust my guess and replace the 4 with something bigger and heavier, its partner will correspondingly be smaller and lighter. So there's a balancing act here, and the teeter-totter will be perfectly balanced only when your guess is exactly equal to the square root. Otherwise, there's going to be a low end and a high end, right?
Right. And I just want to explain what I meant by not linearly. What I meant was 4 times 9 is 36, but we can't go up 1 from 4 to get 5 and down 1 from 9 to get 8. 5 times 8 is not 36. So that's what I meant by it. It's not going to be a linear progression.
Right. And in fact, the actual functional relationship between these two quantities is captured in the expression y equals 36 over x. So it acts like this hyperbola, this 1 over x kind of shape, which is definitely not going to be linear. So that's a good call out.
Well, thank you very much.
So now we've got a 4 and a 9, and we know that they are acting as lower and upper bounds. The actual number that we're looking for is somewhere in between. This is something akin to your opening guesses for the square root of 91, right? You said, well, it's going to be between 9 and 10. And then you just picked 9.5 because you said it's right in the middle. Let's go with 9.5. Right. Well, you know what we're going to do? Pretty much exactly that. We're going to take the average of the numbers 4 and 9.
I had a feeling you were going to say that. And so while you were saying it, I already thought about it in my head and got that the average of 4 and 9 is 13 over 2, which is 6.5. So it's going to still be a little too big.
It is too big, but notice that it's a much better approximation than 4 was. So when you squared 4, you got 16, which is a full 20 units away from 36, right? And if you square 6.5, in other words, 6.5 times 6.5, you get 42 and a quarter. And that's a lot closer to 36 than 16 is.
Yeah, we're honing in on it.
And now, as you already noticed, 6.5 can be expressed as a fraction, 13 over 2. And herein lies the explanation for how I got that crazy fraction at the beginning of the episode. I was employing this algorithm and I just kept track of the fractions as I went.
I see. So I'm going to guess that the next step now is going to be to figure out what 6.5's multiplicative partner is to get us to 36.
You are 100% right. That's excellent.
Awesome. All right.
Now,
I'm not going to do that in my head. I'm going to do that here on my computer. And 36 divided by 6.5 is giving us, well, it's not a whole number, but it's 5.53846, and it goes on for several more decimal points.
Yeah. And in fact, it does go on for several more decimal points, but let me read a few more of them out so that listeners can hear what is happening with these decimal points. Okay.
All right.
It goes 538461, 538461, 538461, and so on and so on and so on.
Interesting. So it's a decimal with a repeating pattern in it.
Exactly. And we know that that's true of rational numbers in general. If you take a rational number, in this case, that number is 5 7/13, or if you prefer, 72 over 13. Anytime you convert a rational number into a decimal, it will have a repeating expression. Unless it's either exact or it's a whole number, it will have a repeating pattern to it. And in this case, that repeating segment is 538461.
That's cool. And I also can't help but notice that we just determined that the multiplicative partner of 6.5 is just a little bit over 5.5. So 6.5 times about 5.5 is going to give us 36. And if we take that average of 6.5 and just a hair over 5.5, we're going to get pretty close to 6.
Yeah. And you could imagine that every step you take in this algorithm, you get even closer, and that this algorithm is unlimited in the sense that you can always keep going. It's like a machine with a little crank. Like, oh, you want another approximation that's better than the one you already have in mind? Great. Drop the number in and turn the crank, and I will give you that next number.
So how did you decide when you were computing the square root of 91 when you had gone far enough and you were going to stop?
Well, two reasons. One, my family was yelling at me to get back to the movie, which is really That's really the compelling argument. But mathematically speaking, I looked at the numerator, 14,767, and I was like, oh no, this is done. I am done. There will be no more approximations tonight. Right. So
I don't blame you or your family for the decisions made in that moment.
yeah, I have gotten in trouble maybe once, twice, or a million times for this kind of thing. So I'm not sure I've learned my lesson.
I want to come back now to that question that I put on hold a few minutes ago, where I said, how useful is this algorithm really if it doesn't give you an exact answer? And I can see how useful this algorithm is. It doesn't give you an exact answer, but it really gets you close. And the more you're willing to crank into it, the closer it's going to get you.
Yeah. Now, with a number like 36, I mean, frankly, we can figure out what the square root is. I mean, even with a number like 529, which happens to be a perfect square, you could try a few things to see right off the bat if it is a perfect square. And you could use your calculator and it would tell you that the square root is 23. You could probably figure that out even by pencil and paper, right? But that's not really the value of this algorithm. The value lies in that infinite set of numbers that are not perfect squares. And you can imagine, just to sort of go back to, hey, we're building a rocket and we need to land on Mars. There are going to be some square roots that come up in that engineering work, right? And they're not going to involve perfect squares, but you're going to need to be very accurate because you're building some part for the rocket ship, right? And you need to have very precise measurements. That's where this algorithm shines.
I see. Yeah, that makes a lot of sense.
Now, just to complete the story here for the square root of 91, I mean, this is part of why I got yelled at too. I was writing a little Twitter thread about how I did this. And so my family was really like, dude, put the Twitter down now, or we're going to take your computer. But I wrote up my calculation on Twitter so I can look at it right now and see where I started my guess at. And I started with 9. I used 9 as the input value. As you noted, the answer is bigger than 9 and less than 10. And so I just said, well, let's choose the biggest whole number that's less than the value that I'm looking for. And let's use that as my starting point.
That makes sense. So this algorithm works really well, but it's also helpful to use it hand in hand with some number sense and some educated guesswork.
Exactly. And of course, I chose the number less than the target, right? I chose 9, which is less than what the square root will be. You could equally well have started with 10, right? Like, why not? 10 is as good a choice. In fact, what's cool about the algorithm is you could always start with 1. It doesn't matter. You could, if you just didn't even want to think about it, I'm just going to guess 1. Clearly a bad guess, but the algorithm doesn't care. It will still work.
It seems like the only starting guess that would be invalid would be 0, because you can't multiply 0 by anything to get to that target.
Right. 0 doesn't have a multiplicative partner, right? What is 91 divided by 0? You can't do it. And of course, negatives are off limits too.
I was just wondering if negatives were off limits, and I wasn't sure if they would be or not, because -3 has the same square as +3. So 9 actually has 2 square roots, 3 or -3, but this algorithm would only get you to 3. Or if you started with a negative guess, it would get you to -3, wouldn't it?
It would actually, now that you mention it. At least I'd want to check the details in the privacy of my own home, as the saying goes. But yeah, I think that's right. I think if you started with -9 as your initial guess and you ran through the algorithm, I think it would take you to -9.53, et cetera, et cetera.
So negatives aren't necessarily off limits. They just sort of are going to give you a different kind of an answer. They're going to give you the negative answer instead of the positive answer.
Yeah. Now, just as a point of clarification here, technically, when we talk about the square root of a number, like we say, what is the square root of 91? Implicit in that question is the fact that we want the positive number whose square is equal to 91. But of course, in general, there are 2 numbers that will square to a given number. So if I said to you, Noah, x squared is equal to 91, solved for x, then the answer there would be plus and minus 9.53, et cetera. So there's value here. I hadn't thought about it before, but you're right. You really could start with negative numbers to find that other root.
I'm glad I was able to help.
There's a reason you're my co-pilot on this crazy adventure.
Should we be writing to any mathematical journals about my new discovery?
I'm going to say definitely no. Okay.
Okay.
We can talk about that offline. All right. So I started with a guess of 9. I computed the algorithm, turned the crank, so to speak. And the first approximation that it gave me is the fraction 86 over 9.
Well, that comes to 9.5555555556.
Okay. I'm guessing that the 6 is rounding up because it's in
I'm
increments of
guessing it is, Joe. I
5.
think it's going to be an infinite series of 5s, probably.
And that makes sense because 86 over 9 is really 9 and 5/9, and 1/9 is zero point 0.1 repeating. So just multiply by 5, and now you've got 0.5 repeating. Okay, so even that first guess is pretty good, right? You go from 9 to suddenly having 9.55555. And we know the answer is 9.5394 something. So pretty good, right? Well, then I took 86 over 9 and plugged that in. And that's how I got 14,767 over 1,548.
Okay. And I'm assuming if I put that fraction into my calculator, I get something very close to the value you got of 9.539405, et cetera, et cetera. And looking at my calculator, I got 9.5394056848. Cool.
Yeah. Now you may wonder, when we started with 36 and I said, hey, Huron's method will never get to the exact answer. We do know that with 36, there is an exact answer. The answer is 6. So you might wonder, well, what about for the square root of 91? Is there some other way to get at, quote, the exact answer? And I guess my question for you, Noah, is what do you think? Could there be another mechanism?
I can't say that there can't be another mechanism, but I am going to say I don't think there is an exact answer because I think this is an irrational number where the decimal never ends. So there's no exact answer.
You're right. There is no exact answer to be found in the sense that we cannot write down a closed form decimal expression of what the square root of 91 is. I mean, if you want an exact answer, you write 91 and you put a little square root sign over it. Bing, you've got the exact answer.
Or the fraction that you came up with.
Yeah, but even that's an approximation, right? Like 14,767 over 1,548. That is not exactly equal to the square root of 91. So what is super interesting to me about this is, well, there's a couple of things. First of all, I love the fact that there is a process that you can carry out by hand for approximating square roots. Now, the old timey word that people used to use is called extraction. So we'd say square root extraction. That's the process of generating an approximation to a square root. But typically, we all grow up thinking like, oh yeah, just use your calculator, right? Well, how does the calculator do it? This is one way to answer that question. Something like this. So that's very cool. And as we continue marching into the future here and we offload more and more of our intellectual work to computer systems like ChatGPT, there is something refreshing about this kind of hand calculation, right? You don't have to say, hey, Alexa, or hey, ChatGPT, what is the square root of 91? You can say, I don't need you, little robot crazies, because I can compute it myself. Thank you very much.
Oh, okay. Whatever. So next time you need someone to perform simultaneous floating point variable calculations in 4-dimensional space to coordinate a time jump so you can rescue your dorky little measuring cups, I'll let you compute it yourself.
Nice. Something I was thinking a minute ago. Your calculator is not doing exactly this process because when you type in 36 and hit square root, it will give you the exact answer of 6. So it's using some kind of algorithm that gives it an exact answer in that case.
Yeah. And you could look up exact algorithms for how modern day computers calculate square roots. In fact, there may even be an IEEE specification for how to compute square roots up to some known accuracy, right? But I will say this algorithm that due to Heron of Alexandria, it converges quadratically, which means basically every time you turn the crank to get another approximation, you've now doubled your accuracy. It gets twice as many digits correct with each turn of the crank. So that's a very fast converging algorithm. And for people who know calculus, they may be thinking, well, what if I took a Taylor series approximation and tried to compute the square root of x that way? It's going to be a lot slower. It's really hard to beat this method, which for those of you who are interested, this is the method that Newton's method generates for the function x squared minus 91. That root finding method is essentially this one. So there's Newton again. We can't escape it.
And why would we want to? Well, Pete, this has been a super fun conversation about square roots. I am really excited to be back in the math club with you for a new year. And I think we have a little announcement we want to share with listeners before we wrap up this episode.
Yeah, I'm happy to be back in the math club with you as well. This was fun. I love it when math problems sort of come up in the wild, if you will. And this problem came from Leo. I certainly didn't know that going into the movie, but I just love it when a little math pops its head in and says, hey, hello, I'm here. But yeah, why don't you share with listeners sort of our thinking about the coming year?
All right. So Math Club, as we said, we're happy to be back and we're looking forward to bringing you lots of great mathematical episodes in 2024. But there's going to be a change in our release schedule that we wanted to make you aware of. Up until now, we have worked really hard to put out an episode every 2 weeks, and that has just gotten to be a little bit stressful at times. So we're going to continue to make episodes and put them out, but we are not going to be holding ourselves to such a tight release schedule. Our plan is to make episodes as quickly as we can without sacrificing our sanity or our work or our families. Does that about cover it, Pete?
Yeah. I mean, it is surprising probably for some folks to know that you and I don't just hang around the math club all day, just dreaming up episodes. Like we do have other things going on. And, it's about striking a balance because we love this show. We love this community and we want to keep doing some great stuff. We also need to, maintain all the other parts of our lives too. So I think it's going to be a good year. It's going to be slightly different pacing, but I think it's going to be more of the same kind of great math episodes.
And with that, we wish you all a happy new year and we'll see you next time.
Happy New Year, Math Club. Later.